Hi everyone, I am Siddharaju, Assistant Professor of Chemistry. In this session, I am going to explain about the electronic effects, particularly about the hyperconjugation. It is there in the syllabus for the BSc first semester and the title of the paper is Chemistry 1 DSc 2A. Let us consider hyperconjugation. It is a general stabilizing interaction. It involves the delocalization of sigma electrons of CH bond of any alkyl group directly attached to an atom of unsaturated system or to an atom with unshared p orbital. That means sigma electrons of CH bond of any alkyl group can enter into the partial conjugation with an atom of unsaturated system or with an atom having unshared p orbital. Hyperconjugation is a permanent effect. It is also called as no bond resonance. The concept of hyperconjugation can be better understood by considering an example of propene. Look at this molecule. Here the CH3 group is directly attached to the unsaturated system. That means CH3 is attached to a carbon having double bond. Among these two bonds, one is a sigma bond and another one is a pi bond. As we know that the pi bond are formed by the sideways overlapping of unhybridized p orbital of this carbon atom and this carbon atom. And these p orbitals are perpendicular to the plane of this carbon-carbon sigma bond. Here, the carbon having a double bond is in turn attached to the CH3 group. This CH3 group has 3 carbon hydrogen sigma bonds. This is one carbon hydrogen sigma bond and this is another carbon hydrogen sigma bond and this is one more carbon hydrogen sigma bond. Among these 3 carbon hydrogen sigma bonds, one of the carbon hydrogen sigma bond lies in the same plane of the p orbital forming a pi bond. As a result of this, the sigma electron of this carbon hydrogen bond interacts with the p orbital and this is what we call hyperconjugation or no bond resonance. The hyperconjugation stabilizes the molecule. As the number of hyperconjugation interactions increases, the stability of a molecule will also increases. So, the concept of hyperconjugation can be used to explain the stability of alkenes. Let me consider that. Here I am taking 3 alkenes. One is propene, another one is ethene and one more is 2-butene. Here you consider propene. The CH3 group is directly attached to the unsaturated system. Hence, this compound can show hyperconjugation and it can be explained as follows. So, here in methyl group CH3 group, there are 3 carbon hydrogen sigma bonds. If I say this carbon hydrogen sigma bond is involved in the hyperconjugation, this is what the no bond resonance structure we are going to get. If this carbon hydrogen sigma bond is involved in the hyperconjugation, then this will be the no bond resonance structure. If this carbon hydrogen sigma bond is involved in the hyperconjugation, then this will be the no bond resonance structure. Totally, we can write 3 no bond resonance structure for the propene. As a result of this, propene becomes stable molecule. Now you consider ethene. In the case of ethene, there is no methyl group attached to the unsaturated system. Hence, this molecule cannot show hyperconjugation interactions. As a result of this, ethene becomes less stable when compared to the propene. Now you consider one more molecule, that is 2-butene. Here, 2 methyl groups are attached to the unsaturated system. One methyl group to this carbon atom and another methyl group to this carbon atom. As a result of this, 2-butene can show 6 hyperconjugation interactions. So, as the number of hyperconjugation interaction is more for the 2-butene when compared to the propene, 2-butene gets stabilized. It is more stable when compared to the propene. This is how we can use the concept of hyperconjugation to explain the stability of alkenes. Let me consider one more example, CH3CH2 plus ethyl carbocation. Here, methyl group is attached to the carbon having a positive charge. The carbon with positive charge is having unshared p orbital, and this p orbital is perpendicular to the carbon-carbon sigma bond. And this carbon having a positive charge is attached to a methyl group. It is having 3 carbon-hydrogen sigma bonds. Among these 3 carbon-hydrogen sigma bonds, one of the carbon-hydrogen sigma bond lies in the same plane of this p orbital. Hence, the sigma electrons of this CH bond can interact with the p orbital, and this is what we call hyperconjugation or no bond resonance. Hyperconjugation stabilizes the carbocation because the electrons of the sigma bond helps to disperse the positive charge on this carbon atom. As the number of hyperconjugation interactions increases, the stability of carbocation will also increases. So, the concept of hyperconjugation can be used to explain the stability of carbocations, or it can be used to compare the stability of different carbocations. Now, let us consider this. Here, I have taken 3 carbocations. It is tertiary carbocation, it is secondary carbocation, and it is primary carbocation. So, it is tertiary butyl carbocation, it is isopropyl carbocation, and it is ethyl carbocation. So, in the case of tertiary butyl carbocation, the carbon having a positive charge is attached to 3 methyl groups. As a result of this, the tertiary butyl carbocation can show 9 hyperconjugation interactions. In this case, the carbon with a positive charge is attached to 2 methyl groups. As a result of this, it can show 6 hyperconjugation interactions. Here, the carbon having a positive charge attached to only 1 methyl group, so it can show only 3 hyperconjugation interactions. As we know that as the number of hyperconjugation interaction increases, the stability of carbocation will also increases. So, these carbocations are following this order. Tertiary carbocation is more stable when compared to the secondary. Secondary carbocation is more stable when compared to the primary. This is how we can use the concept of hyperconjugation to explain the stability of carbocations. Let me consider one more point, bond length. We can use the concept of hyperconjugation to explain the bond length, particularly in the case of propene. Look at this molecule. It is having one carbon-carbon sigma bond and another carbon-carbon double bond. The standard bond length of a carbon-carbon single bond is 154 picometer. But in case of propene, the bond length of carbon-carbon single bond is 149 picometer. It is not 154 picometer. It can be explained by considering hyperconjugation as follows. You look at these structures. Here, the methyl group is attached to the unsaturated system. The sigma bond of this carbon hydrogen can involve in the hyperconjugation interaction. As a result of this, the carbon-carbon single bond is going to have some double bond or partial double bond characteristics. As a result of this, the carbon-carbon single bond length decreases from 154 picometer to 149 picometer. This is how we can explain the bond length of carbon-carbon single bond in case of propene by considering hyperconjugation. These are the important concepts to be considered in the case of hyperconjugation. Hope you understood them. Thank you.